Kevin. All right. The first, there is some big important update about our final date. Yes, Kevin, find some place called a web stack. Yeah, web stack. Find the official time. Yeah, because the reason when I made my syllabus, I didn't know. I searched the web, but I couldn't find where to find the official time. So I just used a convenient time based on my, judgment. Yeah. But, so, later I changed to May the 2nd. But now, this official time is May 7th, Tuesday, our class time from 6 to 8, 2 hours class time. Okay? So this is a big update. Yeah. Please arrange your plan, yeah, because some students, they need to, take a day off, right? Especially for those students, take a day off. So you need, yeah. So here we have more than 2 weeks, right? Yeah. So that's nice thing. More than 2 weeks. Yeah. Oh, let me ask you, for reading and the final, do you know we need to meet or not, or we do not meet? So
for reading week?
Yeah, reading week. No meeting, right?
I'm not sure. I think it's more of just a study week.
Yeah, study week. Yeah, as I understand, also study week. Yeah, so no meeting, right? Yeah, no meeting. Yeah. So then I will not give you classes review. Yeah. So for that reading week. Yeah.
I think we just be review days.
Review?
Yeah, just Tuesday to Thursday. Just reviewing the final.
Reviewing final.
For the second and
Was it the 30th?
yeah, the 30th and the second.
30th and the second 2 days. Yeah. Review. All right.
Usually like practice problems.
Practice? Oh, yeah. Okay. Yeah. Yeah. We can think about that. Yeah. We can. Yeah. So we have some freedom to decide how to do. Yeah, definitely, I can. First review. I can explain some common problems, right? In my grading, concept things, I can explain. After that, I may give you some sample questions. You can practice, whatever, Yeah, but that's optional. Yeah, for our students, it's optional. Okay. So if we want to practice, that's good. Yeah. All right. Yeah. Okay, yeah, so that's the big change. So tonight I will send out announcement to update this important date, and also I update my syllabus. Yeah. Update my syllabus. Okay, web stack. Yeah, web stack. Okay, yeah, that place to find this information. Yeah. All right. Yeah. So let's continue. Yeah. The Fourier transform. Yeah. Yeah. Today, so let's finish the definition of the Fourier transform. Yeah. So then we can do the recovery session. So today, I like to do only one problem, number 19. How about that? Yeah. One problem. Next time, another problem. Yeah. Because the last problem pretty long. So each time you just do one. Yeah. Otherwise, it takes too much time. You do 2 questions. Yeah. All right. So save your time a little bit. Yeah. Yeah. Oh, another thing, because you talk about the reading. Yeah, so if we still meet, so probably I still give students recovery sessions so they can pick up some points if they like. It's optional. Yeah. It's optional. Yeah. Okay. Yeah. All right. Yeah. So let's start from what we left in the first half. All right. So we are here. Okay. Yeah. So we are here. Right. All right. Yeah. So here. Let me see. Yeah. So let's recall a little bit, okay, the whole story, because we stop in the middle, so the whole story. Yeah. All right, so what we are doing here, so I said inspiration. Yeah. So here I'm talking about researchers, how they discover new results. Yeah. So, in our human history, knowledge development, we keep developing new knowledge. Okay. Yeah. So the researchers here, in order to get a Fourier transform, yeah, because this is a big invention. Yeah. So people need to get some hints, need to get some, clues. Yeah. Otherwise, nobody is that genius, so they can, suddenly, without any knowledge background, they can define Fourier transform. Right? Why you do that? Yeah. So here, the Fourier cosine, Fourier sine transforms already very close to the Fourier transform. Yeah. But they are real form, okay? These are the real form, but they are not independent real forms, right? Think about it. They're not independent real forms. They are a pair of correlated real transforms. So it's a pair of coexist. In our computation, these two transforms are coexist. We need to use both transforms interchangeably. Yeah, that way. Yeah. All right. So that means there is some rationale behind the scene. There should be some integral form to combine these two kernels, sine function kernel and the cosine function kernel. We combine them. Yeah, yeah, because they always appear in a pair. Yeah, that means they should work together. Right? Yeah, they should work together. Yeah. So the natural way to combine sine cosine E function, the Euler formula E function. Right? Yeah, that's the natural way to combine these two functions. Yeah. All right. Yeah, so that's the, that's our understanding. Yeah, so that's some understanding here. All right. Then, to combine, we need to do calculation. Okay? Yeah, we need to find a natural way to combine them. So the calculation, yeah. Here, the calculation we are doing here, we try to combine these two transforms to form a new integral transform. Just one transform, okay? One transform, we cover the general case. We cover the general case. Yeah. All right. Yeah. So after that, then we make some comments. Yeah. All right. So here we start from the original formula, but our original formula, certain symmetry is required. Okay? Even function, odd function, certain symmetry is required. Yeah. All right. So when we work, in order to go from special cases to general cases, we want to remove the symmetry. Now, we want to, extend our formula to non-symmetric functions. Yeah. All right. So here, the first time we combine, we just do it. Okay. Yeah. So we just do it. Okay. Yeah. So many mathematicians, when they work on the formulas, yeah, we know sometimes the formulas may not make sense. Yeah, because the convergence problem. Yeah. Yeah. But sometimes those mathematicians, they just work on it. Okay. Yeah. So they try to see how far they can get. They can go. Yeah. So here, that situation. Yeah. Let's just work on it. Okay. All right. Yeah. So then, the formula change. Yeah. So the change from step by step. Yeah. Very natural, But at this point, when we look at the integral, inner integral, outer integral. So here I'm talking about this place. Yeah, for Zoom size student, inner integral, outer integral here. Okay, the inner integral is on the whole x-axis. That's good. Yeah, because we want to extend f function on the whole x-axis. Yeah, so the inner integral is fine. Okay, but outer integral is on half axis. That's not a general. Okay, the half x-axis, this case not very general. Yeah, because that half x-axis comes from the symmetry. After we take advantage of the symmetry, we simplify full x-axis to half x-axis. Now we want to go back from half axis version to full axis version. Then we can remove the symmetry. Remove the symmetry. Here we don't want to use the symmetry. Okay? So we want to remove the symmetry. Yeah. All right. So that's the next step. Yeah. Yeah. Next step, the outer integral we change to full x-axis. Full x-axis. Now, but you cannot just change, you need to adjust your constant. Okay? Half axis is 1 over pi constant, so your full axis should be 1 over 2 pi. You need to make corresponding adjustment. Corresponding adjustment. Yeah. Yeah. All right. Even, yeah, because some logical reasoning you may jump a little faster, but in your formulation you still need to do rigorous calculation. Okay? Yeah. All right. So now, after you adjust the constant, you change the outer integral to full x-axis, then the whole function, you can remove the symmetry assumption. The whole function f of x, you can assume it's a general function. Okay? It's a general function. Yeah. All right. So, yeah. General function, but we assume the function, because here we do the integral, we assume it's absolute integrable. The function must be absolute integrable. Otherwise, when you take integral, it's divergent, meaningless, right? So you want a convergent. Yeah. So your function is good enough. Yeah. Good enough. How good? Absolute integral. Yeah. So what's the absolute integrable? Yeah. So here, let me write a formula. Absolute integrable. So that is, you take integral on the absolute value of f of x on the whole x-axis must be less than positive infinity. So must be a finite number. That's what we mean. Absolute integrable. Okay? That's the basic requirement for f function. Yeah. All right. So with that, now here we have this form. Yeah. All right. Let's go another step forward. This time, we need to look at the sine part. Sine. Yeah. This one comes from cosine. Fourier cosine transform. Now, we want to do the same thing on sine function. Yeah. Sine function. Yeah, here. Right. So here, we need to use more imagination here. Yes. Here, we need to use more imagination here. Yeah. Because the logical reasoning, you may jump some big steps. You may jump some big steps. Yeah. Why is that? Yeah, here. First, why we have this formula. Yeah. Why we have this formula. Okay. This formula is based on the assumption f is an odd function. Then we have this. F is an odd function. then we have this. Okay, yeah, yeah. If f is not our function, then we don't have this formula. Okay, yeah. All the functions do cancellation, so then we have this equals 0. Yeah. So here, when we try to discover something new, yeah, here we use f odd function. Okay, we use add function. Yeah, but when we get to our destination, we remove that f function odd even assumption. No, we remove that. Okay, yeah, yeah. Sorry, the odd function, not the f odd function. F times sine function is an odd function. Yeah, not f itself odd function. Okay, f times sine function, so it's an odd function. Yeah. We use that. All right. Oh yeah, yeah. Right. Okay. All right. So then we can use the Euler formula. Add these two, but the second one we can multiply I, right? Multiply I, because sine we need to multiply I in front of I. Yeah. So if we put the I here, still 0, right? The integral, here we multiply an I, still 0. Then we can add those two terms. By the Euler formula, we have this E. We have this E function. Yeah. The cosine, sine, right? So the E. So now, this is our destination. Okay? Yeah. This is the most important formula here in this module. Okay? All right. Yeah. So, although some steps may not be very rigorous, we try to. Yeah, so here, follow some clue. So all these things we can treat as clues. Okay, we follow some clues. Yeah, guide us to discover something very valuable. This is the most valuable formula. Okay, this formula is extremely valuable. Okay, so all those clues so guide us to get this, this gem. Okay, yeah, this gem. Yeah, 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 yeah. Otherwise, without those clues, how do we know this, right? Nobody knows you can write that way. Yeah, it's hard to prove it. Yeah. So here, that's how people discover new knowledge results. Yeah. So, all right. After that, based on all the background information, in this formula now we can remove any symmetry from F. Right? We can remove any symmetry on F. Okay, yeah, because we want to apply this formula on the general function F. Now, how general? Absolute integrable. Okay, absolute integrable. Yeah, that general. Yeah. All right. So now, with this most important formula discovered, next we can define Fourier transform from this formula. Both Fourier transform and inverse formula are built in this one formula. Okay, this one formula gives us both Fourier transform and inverse Fourier transform. We just split this integral in the middle. Okay, yeah. So here, yeah, because we did similar things before. So here we split this formula in the middle. The inner integral gives us the Fourier transform. The outer integral gives us the inverse Fourier transform, so we can recover the original function. Yeah, yeah. So that's the essence of this formula. Yeah. All right. So next, let's look at the formal definition of Fourier transform. Yeah. All right, C.4, Fourier transform and inverse Fourier transform. Fourier transform. We start from the complex Fourier integral. This is complex Fourier integral. Yeah. So one integral, okay? Yeah. So we, yeah. And here we do not assume any symmetry. Yeah. So any symmetry, no symmetry. Yeah. But we assume f is absolute integrable. Okay. Absolute integrable. Recall Fourier cosine transform. Yeah. So we did similar things in the Fourier cosine transform. Yeah. Yeah. So this is our, Fourier integral. Yeah. When we define Fourier cosine transform, we start from Fourier integral like that. Okay. All right. Then we replace capital A function by its integral form. So we get this double integral formula for f function, cosine. Yeah, yeah, double integral. Then we split this double integral two halves. The first half, the inner integral, that is our Fourier cosine transform, inner integral. Right? Then we have outer part, outer, inner. Continuation, inner, outer, the inverse Fourier transform. So one integral we split into two halves. One normal integral, a normal transform, another inverse transform. Yeah. So here we follow the same approach. Yeah. But this time we split this integral. Okay? Yeah. That big integral. Yeah. All right. So the Fourier transform inner integral. Notation, f, this little veg symbol. Yeah. Constant, we take root. 1 over root of 2 pi. Okay? Yeah. So here. Yeah. Yeah. All right. Then integral from negative infinity to infinity, our f function, the kernel. Okay? This kernel e function, there is an I with it. Here you need to feel comfortable with the complex I. Yeah. Complex. Yeah. Yeah. So here you may ask yourselves why people use the complex numbers expressions in this situation. Yeah. Because when you calculate the Fourier transform of f function, f could be the real function, right? F usually we use a real function. But then when you calculate the Fourier transform, usually this is a complex function. Yeah? Because your f function, we assume no symmetry. F no symmetry, then f is a complex function. Okay? You cannot assume f is a real function. Yeah. But if f has some symmetry, that's different. Think about it. Yeah. If f is an even function, then we take its Fourier transform. Can we say its Fourier transform is a real function? F is even function. Even function. Sine, cosine, okay? Cosine, sine. Sine times even function cancel out 0, right? Yeah. So the imaginary part becomes 0, okay? When f is an even function, the imaginary part becomes 0. So then f function becomes a real, in that f Fourier transform, f hat function becomes a 0. Yeah. All right? Yeah. Yeah. Similarly, if f is an odd function, what do you get? If f this time is an odd function, what do you get? you will, this time the real part is gone, right? The real part, yeah, because all the function, the real part equals 0, so you have a pure imaginary function, right? I times a real function. So you will get a pure imaginary function, okay? But in general, if f is not even, not odd, you just get a complex function. It's a complex function. Yeah. All right? Yeah. Okay. Yeah. So that's the Fourier transform. Yeah. Next. Yeah. So we use this Fourier transform notation. Okay? Yeah. Yeah. Short notation. Yeah. So when we do calculation, inverse Fourier transform. Yeah. All right. F of x equals, yeah. So this time the outer integral part. Okay? Yeah. Yeah. But the function, f function, this time becomes the Fourier transform of the original function. Yeah. All right. Yeah. Yeah. So here you can see in the Fourier transform, your e function, you use the negative IWX. For the inverse Fourier transform, the e function, you do not have that negative. Okay? You use e to the IWX. Yeah. Yeah. So that, that different. That's slightly different. Yeah. That difference. Okay? Yeah. That difference. Yeah. All right. Yeah. So that's the famous Fourier transform. Yeah. Inverse Fourier transform. All right. Yeah. So next, the last slide of today, properties of Fourier transform. Properties. Yeah. All right. Yeah. Existence of Fourier transform. Yeah. The first theorem. We need to know, given a function, its Fourier transform exists. All right? Here, okay. If f of x is absolutely integrable on the x-axis, yeah, so that's the condition I wrote on the previous slide. Absolutely integrable, yeah, yeah, on the whole x-axis, and the piecewise continuous on every finite interval, then the Fourier transform of f of x given by 6 exists. Yeah, so we know our standard formula exists. Yeah, so that condition. Okay, yeah, there's some continuity. Yeah, yeah. Yeah. So you can see this condition is very weak. So very easy. Our usual real-world functions satisfy this requirement. Yeah. All right. Yeah. So here, the definition of the Fourier transform exists. All right. Then linearity property. Yeah. So Fourier transform. Yeah. It's very natural. The integral, that integral. So when we do this, linear combination. Yeah. That's obvious. Yeah. All right. Then for the derivative. Yes. For the derivative. Derivative, so we can just take a derivative, apply on that original signal, not signal, original formula, yeah. So we can easily prove this one, okay? Yeah, right. So here you can calculate Fourier transform of the derivative in this way, integration by parts, right? Yeah, but definitely you need to, make some assumptions. Yeah, make some assumptions. Yeah, yeah, yeah. But yeah, because think about when you do integration by parts, when x evaluated at infinity, negative infinity, positive infinity, right? Yeah, yeah. Think about that, But negative, so here, yeah, so, yeah. then let's try to understand this part. Do you worry about x approaches positive infinity and negative infinity here? Do you worry about that? Yeah. Actually, we don't worry about that. Why? Yeah. We don't worry about that. Yeah. The reason is very simple. No matter x approaches positive infinity or negative infinity, you know e to the wx real number, right? Wx real number. Its absolute value is 1, right? Yeah. Always 1. Okay? No matter what the number wx is, yeah, because it's an imaginary number, imagine absolute value always 1. Okay? Yeah? Because we know e to the negative I wx equals cosine wx plus I sine wx. Absolute value just, cosine square plus sine square, take the root, right? That's the absolute value, yeah, for the complex number. So it's always 1. So you don't worry about that. But for x part, we assume 0, okay, for x part. The limit, when x goes to infinity, the limit is 0. Yeah. Yeah. That's very easy to see, yeah, because when fx is square integrable, and it's continuous on every finite interval, with that condition, we can easily get the limit goes to 0. Yeah. Otherwise, we can get contradiction on the square integrable. Okay? So if you not 0, if you're a little higher, we have positive area, right? Yeah. So we can force it. The limit must be 0. Yeah. So this part, yeah, integration by parts, so we can do at the 2 limit bounds, limit must be 0. Yeah. All right. So we can, yeah. All right. Get that formula. Then apply this formula twice, right? Double we apply twice, so we can get that. Yeah. Just do it twice. Yeah. All right. Yeah. So let's stop right here. So after this class, let's see. After this class, next week we have 2 classes. The first class, I like to talk about, the digital, cosine transform, digital Fourier transform, digital cosine Fourier transform, and a fast Fourier transform. Yeah, another important topic. Yeah. All right. So after that, so I may want to talk about one. I try to I try to finish. I try to finish the whole module on Tuesday. So Thursday we do review. Okay. Thursday we do review. Tuesday we the last part of module 5, part D, the last one. So then Thursday we do review. Yeah. Okay. Yeah. All right. Yeah.
Homework 3 is coming this weekend.
Yeah. Homework 3. So tonight, tomorrow. Yeah. I want to. Make it available tomorrow morning. Yeah. Tomorrow morning, Friday. Yeah. So give you 1 more week to complete. Yeah. So the next week, the whole week. Next week, the whole week. Yeah. Then in our reading week. So you need to submit in our reading week. Yeah, reading week. Okay, so reading week right now I'm targeting Tuesday. Yeah, I'm targeting Tuesday. Okay, so Thursday we have chance. If we need to do something, we can still do on Thursday. Yeah. So still optional, you know, meeting time. Yeah. So then May 7th, so then the final. Yeah. All right. Yeah. So let's move to our recovery session number 5.